torso.
This one, right? Thanks. Okay, let's start, guys. So last time I wrote down the definition for blocks higher child groups with the intent to connect it to motivic cohomology. But similar to the problem of child groups. I mean, this is kind of a geometric definition. So it's difficult to work with it. Difficult to do anything. Especially since we're moved away from the projective case, so we don't have the moving lemma anymore, so you basically cannot do anything. And that's one of the reasons why we passed from DG, DM geometric motives to some sheaf theoretic motives with Nisnevich cohomology. So similarly to here, to study these block higher child groups, we need a sheaf theoretic version of the analog of, let's say, ZTR, which is a sheaf, but that is more closely aligned with these blocks higher child groups. And kind of the answer is to cut up these block higher child groups in terms of dimension. So you look at the case where you have a subspace of a fixed dimension. So the sheaves that we're going to talk about are called equidimensional. Sheaves or equidimensional cycles. So here's the definition. And also now we've been talking about working in smooth separated schemes. And as I said, in a couple of weeks ago, the whole theory is done very generally, and we won't do the very general case because there's just too much to deal with, extra kind of noisy details. But now I want to switch to at least finite type. So from now on, X will be a scheme of finite type over K. And the reason for this is I want to touch on, so in the smooth setting, we dealt with the natural kind of topology which helped us, or the natural site was the Nisnevich site. And for when we move away from smoothness, we need a new kind of site. And this site is pretty popular, among K theorists. It's called the CDH site, or the CDH topology, and also introduced by Vygotsky. And the reason why I'm adding an extra layer of maybe abstractness, moving away from smooth separated to finite type, is I want to force us to have a look at the CDH topology, which is useful for K theory things. But first, let's give the definition of equidimensional cycles. So definition. So this will be some sheaf theoretic version meant to capture blocks higher child groups somehow. So definition of, say, let's call it equidimensional cycles. And again, X is a scheme of finite type. So for R, a positive integer greater than 0, I want to define some pre-sheaf a priori. It's denoted in the literature by Z equi for, well, the definition will be explain why this is equidimensional. So as a pre-sheaf on, just for now, our category of smooth separated schemes, even though X is finite type, but let's just put it on here. So the definition is I take my U in smooth separated, and I need to output what it should be. What is a section of this? So this will be all closed irreducible well, the usual thing, you want to have some kind of cycle in u times x, which over u, so the projection, previously, like we had, when considering the smooth story, we had a correspondence of finite type. Of finite correspondence. But here, I want to just say the following. So, either all fibers are empty, or it is of dimension r. So in the sense that all fibers are either empty or of equidimensional, of dimension r, here r appearing here. And maybe like there's some technical condition where you want to make it surjective on some irreducible component so you don't get some kind of degenerate cases, let's say. Okay, so let's have a quick look at what this means for z equivalent x of 0, let's say. Before I continue, I've defined it on what a section should be, right? But appreciate if it's not just sections, I also need to give you morphisms. If I have a morphism U1 to U2 of schemes, smooth separated schemes, then I should give you a recipe to go from, let's say, equidimensional of dimension r. So careful, like in all previous notation, like some index referred to a codimension, here it's referring to a dimension. But anyway, so I should give you something like a way to map from here to here, so that I actually have a functor, which is a presheaf, right? And the natural candidate is just to pull back. So like I have z here, which is a Levsian u2 times x, and then I pull back along this map. So pull back to give something in here. And of course, like you can always do the naive pullback. And remember, like if you write down what pullback means, you need an intersection product somewhere. So you always have to be careful as to like whether this map is actually well defined. And it turns out that like equidimensional, this property of being equidimensional, it's all intersections are kind of, all relevant intersections are proper. So in some sense, like Z equi is like contained in like these higher block groups. With the relevant kind of index change. But blocks higher Chow groups, they were kind of coming from cycle complexes where we had like a proper intersection along all faces, so that pullback was defined. And here, like, it is well defined. But yeah, the details need to be written out, which I won't do, but it's an important thing to keep in mind here. Okay, let me just continue. I wanted to have a look at the case of when R is 0, but I think I will do it in a couple of minutes. So first thing to note is the following. So remark, I define this Z equi XR as something as a presheaf on smooth K, but actually I can extend it to all of finite correspondences. The sections don't change, right? We're not adding any extra objects. We're just adding maybe some extra morphisms, so-called. But the main thing is this thing still works. And then once you are having a functor from here, it's a natural question whether it's actually a sheaf or something for the Nishnevich topology, and you can prove that Z equi XR is a Nishnevich sheaf with transfer. So in particular, we can apply like Sussman complex to it and things like this. And that's exactly what I want to do now. So definition, I'm going to call this the motivic complex. I will explain why in a second, of X with compact support. So recall the standard motivic complex of X is I take you can define it several ways, but in particular, you can define it several ways now using the embedding theorem. But I can take my free sheaf generated by X, which is the ZTR transfer sheaf, and apply the Sussman complex to it, okay? And that's one definition. But just be careful though, like we've defined this in the case when X is smooth, separated. Now X is of finite time. But anyway, like it's not a big deal to check that ZTRX still makes sense. I mean, you can still pull back things. The main thing is that like you have a strong finite property here. And now I want to define maybe MC of X. So this is of compact support. This, like we've already seen, And the definition here will be, I take the Sussman complex of this equivariance sheaf at 0. Okay, I explained like what is going on here. So first of all, I hope like it's clear that this sheaf ZTRX is contained in Z equi of X at 0. So like what's happening here is that like this is the family of Z, let's say in a section, right? Let's take on U sections. U times X, where U is finite. The projection is finite, right? And here it's on Z X times, U times X, where the projection is now either 0 or of dimension, it's either empty or of dimension 0. So in the literature we call this quasi-finite. So it's either empty or a discrete set of points. And the motivation here is that like a morphism being finite is the same as calling it quasi-finite. So quasi-finite is a priori a weaker condition plus proper. So proper is a stronger condition, of course, but if you are proper and quasi-finite, then you are finite. That's like maybe some fact. So this Z equi cuts out naturally like quasi-finite things, and it therefore naturally forms a functor on what's remaining, like some kind of proper schemes in some sense. So it's kind of the complement of being finite, because everything works well on finite stuff. I know that sounds a bit loose, but essentially like this, when I look at the homology of Z equi via the Sussman complex, it becomes a natural functor on proper subschemes or proper varieties. So what ends up happening is like this is a natural definition for things of compact support, or the natural definition of lower shriek in some sense. That's why we call it MC. Okay. A natural thing to check is the following. So let me just write it as a fact. If X is proper, then the motivic complex attached to X is the same as this MCX. So that basically comes down to what I wrote down before, that finite corresponds to quasi-finite and proper. You just need to write out the definitions and see that, like, yeah, from that factor this follows immediately. But now to actually study, like, for x non-proper, we need, so as I said, like in the smooth case, so in the smooth case, in the case x is smooth, we had the Nishnevich topology. So in particular, like motivic homomorphisms in the DM-GM category was basically Nishnevich cohomology. And whenever you have a site, that's really powerful. Otherwise, when x is proper, when x is just a finite type, there is another site now, which we will define, called the CDH, maybe site, let's say. So CDH stands for completely decomposable H topology. And H, I don't know what that stands for, but it comes from Vygotsky. So basically, the CDH topology, the arguments will be something like, we need to reduce, whenever we have a finite type guy, we need to reduce to something that is smooth. And to do that, we need to do like blow-ups or formal blow-ups. So the CDH site will be some like additional coverings that we put on top of the Nishnevich topology. So let's define it. CDH topology. So here, let S schemes over K to be schemes of finite type over K. So the covers of X are generated, this is a definition, by, so you want to include Nishnevich covers, which are basically just some kind of Ital guys, but more relevant to the K theory, and some kind of formal blow-ups so you can reduce to smooth case. So, smooth case. So the coverings are of the form Y disjoint union Z to X, where we have something like Z is closed inside X and Y sits above it, which is proper. So this looks like a blow-up, like the beginnings of a blow-up square, except this is not at all a blow-up. It's just some kind of formal blow-up in the sense that we just ask for proper and closed, and that away from the closed locus, so X minus Z is isomorphic to Y minus, let's call this map P minus 1 of Z. So it's exactly what happens when you blow up something. When you blow up something along a closed axis, along a closed subspace, you don't change anything on the complement of the open. So in some sense, these are called formal blow-ups. So they satisfy a large section, like collection of good properties of blow-ups, but it's not actually a blow-up. And the idea is that, you can use these formal blow-ups to reduce arguments. Whenever you want to study something about like MC, the motivic compact support, you reduce down to kind of the smooth case, or down to M of X, using kind of these formal blow-ups, and then you're back down to the smooth case, and then you can use results which you already proved for MX, let's say. So these covers too allow one to reduce arguments from MC to MX. Okay, so in particular, you use this kind of strategy to prove the following theorem. So recall that, well, actually, let me just write it down. So here, X is again a finite type. So finite type. And I want to study motivic cohomology or homomorphisms in my motivic complexes. So the setting is as follows. So let F be a Nisnevich sheaf. With transfers. So I can certainly have a look at the following homomorphisms in my category of motivic complexes. I can take the Sussman complex of X. This is just shorthand for the motivic complex, which is just ZTR of X, just in case. I can also take the Sussman complex of F, and typically you add also like some shift to make it as general as you can possibly can. And this is the same as the CDH topology, or of X of this complex. Okay, so this is not a sheaf, right? So this is a complex of sheaves. So I need to resolve it using an injective resolution. So when you do that, you just write a double H. I mean, it's a derived version of, it's hypercohomology in the literature. It just means like, you just need to take an injective resolution of all the sheaves in one go, as opposed to just one sheaf at a time. And another technical thing here maybe is that this C star F, it's naturally a Nisnevich, it naturally lives in like D minus in the category of Nisnevich sheaves with transfer. So we need to, however, this is in the CDH topology, but we can easily pull back from the Nisnevich site to the CDH topology. So in particular, this is getting a bit messy now, but there is a morphism of sites from schemes with the CDH topology, let's say, to schemes with the Nisnevich topology, just by pulling back. Remember, morphism of sites goes in the other direction. So, for example, there is a morphism of sites from the Ital site to the Zariski site. There are more covers in the Ital site. So the morphism goes in the opposite direction of what you expect. So like, you can always pull back as a risky sheaf to make it, and it's a sheaf on the Ital side by pullback, but you can push forward in the other direction. So similarly here, like CDH has more covers than the Nisnevich topology, so you pull back to CDH, and you just add like pull back here, just to make sense of this. So what is like the upshot of this? Like the upshot is that like something we want to study motivic cohomology, which is naturally like homomorphisms in this motivic complex category, which is good. I mean, it's a nice category. It has some sheaf structure, but it lacks a site. Like, you should always try to, even though you have a derived category and even though you have sheaves, that's a great start, something more powerful is to make a site on top of that. Is there a natural underlying site for your objects? And the answer is the CDH topology here. Whenever you have a site, you have a lot more power than just DMEF. So here you can do really like some strong cohomological arguments as opposed to just working in this space. So that's the upshot of this theorem. It's a powerful fact. We already saw this when we were dealing with X smooth. So for example, if X was not just a finite type, but in particular, let's say smooth separated, then this becomes the Nisnevich topology, which was a necessary ingredient even to prove like things like the embedding theorem and the localization theorem. So, I mean, we needed an underlying site to prove those facts, even though maybe we don't remember anymore, but it was a necessary ingredient. But here we just extended the case to finite type things. Okay. We won't prove it, but like we didn't even, to be honest, we didn't even prove it properly in the, well, actually, we did prove some version of this for the case of in the smooth setting when we had Nisnevich topology, and there it was kind of related to the fact that like the complex ZTR, like if I have a Nisnevich cover, U to X, Nisnevich cover, then the check complex that results from it this complex, it was exact. Like that's, I think we proved this at some point, or at least I mentioned it. And this non-formal fact, which we use like some things about the site, right? We use that like something finite over a Henselian ring was like disjoint and things like this. This only works when you have like Ital things or like Nisnevich things. This was exact and it helped us to prove this theorem here in the case of Nisnevich. But CDH, we just use those blow-up covers that I introduced before to reduce down to the Nisnevich case. Okay. Okay, so with this in mind, one final like definition so that we like connect higher Chow groups with motivic cohomology, like we're certainly getting close, is to define this bivariant cycle cohomology. So you can think of this definition as kind of like the glue for block higher Chow groups. And motivic cohomology. But I agree that when I write down the definition, it may seem like a little bit, it's a mouthful in some sense. So here, X, Y are schemes of finite type. And the definition of bivariant cycle cohomology is I also need integer r positive integer, and I any integer, I guess. Yeah. Then this object a r I y x will be the CDH topology at degree minus I of y, and then I look at my equi-complex, sheaf. This is a sheaf, right? Nisnevich sheaf with transfers. I can take its Suslin cohomology, Suslin complex, and pull back to will be again a living in D minus Nisnevich sheaf with transfers, and then I pull back to the CDH topology, and I go like this. Okay, so there's a lot of like indices going on, and like, I think the main thing to keep in mind is like, motivated by the fact that there is a connection with CDH topology, CDH cohomology, and motivic, and some version of motivic cohomology, we want to also vary, like, I mean, we want to study homomorphisms, not just like to some random sheaf F, but like homomorphisms between motive attached to X and motive attached to Y. So this explains like why there's a Y and an X here, like two things. We want to study cohomology, we want to study morphisms from Y to X in our category of motivic complexes. And then like these minus I index, okay, like we don't, this obviously worked out like later on when the proofs happened, but like there's some correct index thing here. And yeah, we want to study blocks higher Chow groups. And as I said, like they are too unwieldy, and somehow the right way to cut them up is to look at it per dimension. And this is the reason why the Z equi appears. But yeah, I mean, I think one needs to motivate why you should write Z equi here. Again, this here looks like certainly very much related to M of C, right? But some higher version, because M of C was R is 0, R equals 0 here, so some higher version of M of C. But yeah, it's not clear like why compact support should appear here and not here. Yeah, it's a bit weird, but it turns out that like with this definition, it's kind of a nice way to state the results connecting, yeah, blocks high Chow groups and motivic cohomology. Let me just say that for now. Maybe like I stated one fact, which kind of generalizes what I just deleted from this board, where like you want to connect CDH cohomology with like morphisms in the motivic complex category, not from X to some random sheaf F, but like from X to Y, or like when I say from X to Y, I mean motives from X to motives from Y. So again, like theorem, this will be a generalization of that fact. So for X, Y now, I want to vary both X and Y, not just X. Then there's a isomorphism between, so in the category of effective motives. So I want to study, again, as I said, morphisms from the motivic complex attached to Y and the motivic complex attached to X. And I want to make this equal to this CDH topology, which is not unexpected, right? Because I had like when a random sheaf F here, I had the CDH topology appearing. And it turns out that the correct way to do it is it's actually equal to ARI of YX. So it'll just be a generalization of the previous fact that I wrote down. But like some nasty things happen, so it's not quite this. So first of all, as I mentioned, like there's this equi appearing here, so it's related to MC. So there's compact support, I didn't really define this, but let's define, C star C of X. By definition, it'll just be C star of, it'll just be MC of X, okay? I mean, I define this to be C star of Z equi X of 0. So there's this C appearing here, which is not unexpected because I have this equi thing cutting out proper things with compact support. And also there's like, because of this dimension I here, there's also some twists in dimensions that one has to take care of. So there's a twist of R followed by a shift by 2R plus I, but that's just details, it's not really important. But the point is like we somehow recovered morphisms in some sense from Y to X using some site, which is a powerful thing. And it's just a generalization again of the previous thing that the previous board that I just rubbed out. And that fact itself was related to, in the smooth case, we had Nisnevich topology appearing, and that just came down to studying the Nisnevich site, so that the complex was exact, the ZTR complex, which I mentioned, the Czech complex I meant. So let's just keep this in mind so that like we can recover ARI, this bivariant cycle cohomology, which people studied in the literature independently of all this, recovers motivic morphisms from Y to X in the motivic setup, which is related to motivic cohomology. Okay. So now I can state the precise, one precise version of Borg's higher child group. So proposition, Borg's higher child groups. So I want to relate this to motivic cohomology, and I keep saying that, but first I relate it to, because of this compact support thing appearing, I relate it to compact support cohomology first as an intermediate step. So in the literature, this is called Borel-Moore motivic cohomology. I guess because in algebraic topology, there is a notion of Borel-Moore cohomology or Borel-Moore homology, and it's just a fancy way of saying look at like prop cohomology with compact support. X will be, let's say just a scheme of finite type over K. And then I have, so for I, there will be two indices, one for the twist, one for the shift. So ij will be some integers. And so I want to study the higher child groups. So there will be some correction of indices due to the dimensions, but it will essentially recover what we want. So we want to study, of course, CH of IXJ in some sense, right? Which is these higher child groups, which I recall is like CHI was like I refers to codimension I, and the jth homology. So like this by definition was the jth homology of my codimension I higher cycles. And this was like, cycles in X times delta I, which, cycles in, So higher Chow groups, remember, were at the ith, in codimension I, we multiply by, delta I, and we take, this forms like a complex, and we take the jth homology of that. So in particular, when J is 0, we recover the usual Chow groups. We want to study CHIXJ, but like due to correction of indices, it will be CHN minus IX J minus 2I, and this is equal to some version of motivic cohomology called Borel-Moore motivic cohomology. So homomorphisms in my category of motivic complexes of Z, I, J, with coefficients in compact support cohomology. So this is in the case if I greater or equal to 0, and some other nonsense in the opposite case. I'm not sure how to motivate like why this splits along different, why the formula is slightly different for different I. I mean, one of them doesn't make sense when I is negative. So for I less than 0. Okay. Okay. So this gives like, so we haven't quite got like motivic cohomology on this side. Remember, like motivic cohomology, we need like X on here and like Z, I, J to be on that side, but it's the kind of the dual in some sense. So we have compact support, so it appears on the other side. So anyway, this kind of homology group, I guess, in algebraic topology is called Borel-Moore motivic homology. and it's an intermediate step to prove that like this thing is honestly motivic cohomology, the block Higher-Chow groups. Let me give an idea of how to show this. So sketch. So I just look at the case where I is greater or equal to 0. So the first thing is the right-hand side. So this thing here, by definition of what these bivariant cyclocohomology was, this is by, I don't know, I just trust the indices that I wrote down here. J minus 2i of spec of k of x. So yeah, I mean, this is just some bivariant cyclocohomology by definition. Now, this Aij minus 2i, it is some CDH topology, but like by some duality with like homology, we use the fact that like we have our complex C star. So let's just take a break from here. I'm not actually continuing on with this equality, but I have my Z equi sheaf in R, and I can take the Sussman complex of it, and then take the this will be some complex of sheaves, and I can take sections in Y, and then I can take the ith homology of this, because the Sussman complex was like going in the negative direction, so we use homology indices. And this is like some object, like it's some homology object, and by kind of duality with in some sense like homology, cohomology, this is equal to ARI of YX. So ARI, like naturally, was defined by like some CDH topology with some coefficients in Z equi, some noise, but like it turns out you can get this equality by as I mentioned, like some version of duality between homology and cohomology, although there is no CDH appearing here, so there is some subtlety. But anyway, let's just take this equality for granted. And so by continuing with this step here, that means that this Aij minus 2i will be equal to the J minus 2i homology of the complex with equi sheaves. So this Z equi xi, matching up all the indices evaluated at spec of k. Okay, so, and this thing we actually can get a handle on. So, so by definition, the degree, so k component of that complex, C star Z equi xi evaluated at spec of k is just equal to Z equi xi evaluated at delta k. because recall like the definition of what C star meant, right? It was treat this as a sheaf and look at the sections of it at spec of K. You just get a delta K appearing at the top. And so this is the group of cycles. Cycles contained in X times delta K, which are equidimensional equal to R, well, fibers over delta K. And it turns out by some results in the Stacks project, or you can find it in the Stacks project. But these equidimensional things, as I briefly mentioned, they were already contained in like they satisfy proper intersections. So in particular, it's contained in these naturally defined block-Higher-Chow groups. So Zn minus I of X of K. So recall, this is equal to, these were used in defining blocks Higher-Chow groups, and this is the group of cycles contained in X times delta K, such that there is like some, that the arrow here is a little bit misleading, but such that intersections along faces, smaller faces is proper. And here, like, we had dimension I, and this explains why we have n minus I here, because it's of codimension n minus I. So in other words, dimension I. So maybe codim n minus I. And the fact that you have an inclusion is, yeah, you can find it in the Stacks project, but it's also a classical result. So we have this kind of monomorphism. So we get a monomorphism of cycles, of complexes. Like on the one hand, calculating equivariant cohomology, so C star Z equi xi of spec of K. So this was somehow, just in case like we've not completely lost, but this was related to the right-hand side of the proposition. And we get a map to, yeah, maybe, yeah, Z n minus I of X of star here, where this star here corresponds to here. And this is a monomorphism. And yeah, then like there was work of Suslin, which introduced their own version of some moving lemma. So somehow they moved cycles which had proper intersection to things which were cut out by equidimensional things. So the upshot is that this thing here, monomorphism, like let's call it capital phi. Capital phi is a quasi-isomorphism. So again, technical work of Suslin by using some other version of a moving lemma. Not the moving lemma coming from projective things that we already covered, but another one. which involves moving cycles which are equidimensional to things that are just proper. Or really the converse, sorry, is a Kazakh isomorphism. And this basically completes the proof. Because on this side here, we end up, well, this is the left-hand side of prof. So this was like blocks, higher Chow groups. And on here, we had like, this Borel-Moore motivic cohomology, or kind of this equivariance thing after we get equated using this bivariant cycle cohomology. So the option, maybe there's a lot going on here, but one way to summarize it is that bivariant cycle cohomology is used as like an intermediate step, as I mentioned, like a glue from going from blocks higher Chow groups, which was used as the very first definition for motivic cohomology, to some version of motivic cohomology, not quite there yet, but some like compactly supported version called Borel-Moore motivic cohomology. But now we have enough to actually prove, the fact that I want. So we get as a corollary. So now let's call this corollary blocks higher Chow groups. This is an important corollary, like I guess historically, because it equates blocks higher Chow groups with motivic cohomology. And it's important because before this story of motives done by Vygotsky, like there was an ad hoc definition of motivic cohomology using these guys. So it was nice to make them equal, I guess. So the statement is as follows. So the block higher Chow groups of codimension I of X with J homology of the complex is equal to motivic cohomology. So H with the correct indices, 2I minus J of X of Z of I, twisted by I. So this guy here, just that I recall, is motivic cohomology. Okay, which by definition is equal to, I just recall, homomorphisms in my motivic complexes, let's GM for now, or could be minus of X of Z of I 2I minus J shift. So that's just by definition. Okay. So let's have a look at the sketch of a proof. So I want, if we recall kind of like, I want to relate this to bivariant cycle cohomology, so I can use the previous fact. So in bivariant cycle cohomology, like I'm not going to recall the entire definition, but we had something which basically had like a CDH topology here. Well, the previous proposition had like HOMs. So this is like the Borel-Moore thing. Or maybe it was definition, I can't remember now. But in any case, like there was something here and there was a CC or here. So I want to replace this ZI with some kind of a compactly supported motive. And the answer is as follows. So I guess remark that if I take affine space of dimension I, of course, if I look at its motivic complex, it's trivial. Like, I mean, it's just Z. But if I look at the compactly supported guy, so this will be the sum motivic, as I defined it, like MC of AI. This is just notation, but just the motivic complex with compact support. Then, like, this is definition, nothing going on there. Then this is actually equal to Z of I to I. It's actually not very difficult to prove. I mean, so a rough kind of guide would be like reduce. So first prove for I equals 1, and then because like you have like a tensor category, it's kind of formal to see that like this when you take products of things, that this is the same as taking tensor product. I mean, everything is like every functor that you have is a tensor functor, which was already verified in the embedding theorem in some sense. So first proof for I equals 1, then plus this fact here, it gives the result for all AI, like the result. So for I equals 1, like we want to show like C star C of A of 1 is basically some part. So Z1 of 2, right? So, but recall like the motivic complex of P1, by definition, it was Z plus Z of this guy exactly. And P1 is already proper, it's projective. So this is also the same as this like motivic complex with compact support. And then you have like some triangle relating like P1, A1 and a closed point, which has Z in it. So this is like somehow the closed point guy related the motivic complex of a closed point, and like what's left is exactly what this thing here is. So anyway, like the upshot, we have this, and so we can replace this Zi 2i. I'm going to put the J out here and replace Zi 2i by CCIAI. So I get that. Let me just rewrite that again. So home of in my motivic complexes of C star X. I'm going to put the J on this side, and I had like I2I here, but now thanks to this remark, I can put like CC of A of I. And now I can use the fact that like, which we didn't prove, sorry, we just stated that like CDH cohomology was related to Borel-Moore thing. So this is equal to I'm not sure of the indices, but I just trust what I have written down here, of 0J of X of A of I. So this equality is coming from, let's say, the relation between CDH cohomology and say, maybe homomorphisms to CC, let's say, which we stated in some previous proposition. And now, by using kind of some property of bivariant cycle cohomology, let me write that, it's getting terrible now. Property of bivariant cycle cohomology. This A0J is the same as A, you can take the X onto the left-hand side, but then you have to switch indices here. I know this looks rather formal because like I'm sure like we're not keeping track of like what these indices actually mean. But anyway, it doesn't matter. The point is like there's some properties which you can prove with bivariant psychocohomology, and it's not unexpected because we have an underlying site. So you can imagine some properties like this are possible to prove. And then by the previous proposition, so basically where we related block high Chow groups to like Borel. This is basically Borel-Moore motivic cohomology, right? So by the previous proposition, this is the same as blocks high Chow groups, X in A of I, J, and then block proved, so by blocks results. So now we are strictly in the world of higher Chow groups. In his paper, when Bloch introduced higher Chow groups, he proved that like they satisfy A1 invariance. So this AI just drops out, and you get CHI X of J. So by, let's say, AI invariance, A1 invariance, which is not unexpected because we certainly did not prove it, but like it's not unexpected because like, yeah, motivic cohomology, like A1 has 0 is trivial. So, but this is in Bloch's paper. So anyway, like we get the result, right? Which is what we want. Okay, great. Let me now make a comparison. So I stated in the previous lecture, I want to compare like what we did in the first half of the lecture. So motivic motives with rational equivalence over K, and like I want to make sure that they sit fully faithfully in this DM, this derived category. So, like a check. Now we have enough like to prove like. Let's check it. So, let's take Y, X, which smooth projective. So these are the guys which generate this category, which are the objects basically. Smooth projective. I mean, the objects are given by, triples like X. I mean, just recall, like a typical object in here is like X, some projector, and some twist R. So let's just take YX smooth projective. Then I want to calculate basically homomorphisms in DM in my derived category, or my souped up category of finite correspondences between the motive attached to Y and the motive attached to X. So this is equal to, first of all, to bivariant psychocohomology by previous results that we proved, by previous results. But recall, like here, X and Y are proper. So like this CC that appears in A in this bivariant psychocohomology, it's just honestly C. So recall, like here, we are using that CC of X is equal to C of X, or the motivic complex, because X is proper. And then by some property of these bivariant cycle cohomologies is the same as putting Y on the other side. We already kind of used it. Dimension, but changing the indices now. 0 spec of K, but putting Y now on the left-hand side. Make that a bit neater. Okay, by property previous proposition, I guess. And by property. Okay. And then this AI was given by Borel-Moore kind of lemma, Borel-Moore proposition. This is equal to higher Chow groups, but somehow the dimensions here match up in a way that actually we get a higher Chow group in kind of homology 0, which is just the usual Chow group. And so this, by definition, was the homomorphisms set, or group, I guess, in our classical Grothendieck category of rational motives, but from, y to x. Maybe from x to y, actually. Yeah, sorry. So maybe, one should write like the opposite category here or something. I don't know. Because recall, when we defined Grothendieck motives, it was like from a functor from opposite category of smooth projective, while it was like a cohomology theory, while for derived category of Voevodsky's motives, it was like a homology theory. So there's some opposite thing going on. But anyway, like this equality proves like fully faithfulness. Okay. Let me now mention one final topic, which is not one final, but for today. Let's get rid of all this So to keep in mind is like we've proven like some powerful fact, like we've related like Grothendieck's motives to Voevodsky's motives. And we had to do that using like the CD, like some CDH site, which was like something not even conceivable when one just looks at Grothendieck motives. So it's quite like we've stacked on like a lot of machinery just to, get a grasp on something that was, defined in a simple way, like Grothendieck's motives, but very difficult to work with in a hands-in way. So I just want to mention maybe the Milnor conjecture. Which is one final application of kind of all this motivic cohomology for today. The Milnor conjecture. Maybe also generalized version of called the Bloch-Kato conjecture. But in this context also called the norm residue theorem. Because this is to avoid the possible confusion with like Bloch-Kato conjecture for special values of L functions, which is another conjecture. So for this, I need to recall Milnor's K groups. So Milnor K groups. So Milnor was interested in like defining like higher K groups. At the time, like it was not clear like what K2 of something should be. I'll talk about like high K theory like in the last lecture, but at this point, like in the literature, like I think 60s or something, I can't remember exactly what year, but like Milnor was interested in like what K2 should be. There was like a definition for K0, K1, but K2 was not clear. And his definition was looking at K2 of a point, so spec of K, and the definition is as follows. So, I'm not going to write K2 out, but like there is a sequence of these groups. So like there is these Milnor K groups. I'm going to get rid of this because it's a bit confusing, but it's just a motivation. The Milnor K groups are these groups which are indexed by R and M on top for Milnor, I guess, of K. So K here is a field. And R is greater or equal to 0. So the definition is K0 of M of K is equal to Z. K of 1 of M of K is equal to K star, and for R greater or equal to 2, Kn of R of K was this R tensor product. So K, the units of K tensored with the units R times. R times. And quotiented out by some ideal IR, which I define now. So where IR is the subgroup generated by A1, A2, AR with AI plus AJ equaling to 1 for some I less than J. Okay, a bit of a strange definition maybe, but like, yeah, I guess you would need to sit down properly and figure out what the motivation is. I can't explain it right now. So the point is, like, all these K groups put together, like this gives a graded ring, which let's call it K star M of K, and this is meant to be equal to the K2, the second K group of spec of K. But it's the correct definition. But anyway, that's just motivation. But anyway, you get this graded ring, and the conjecture is as follows. Well, it was a conjecture, but it was maybe finished 15 years ago, the proof. So it's a theorem now. So there is, wait, what's happening with this pencil? I'm not sure. So there is a canonical isomorphism, I guess. Isomorphism for any L not equal to the characteristic of K, where we take this graded ring of Milnor's K groups and quotient out by L, and this should be the same as the graded Étale ring or Étale cohomology across N of Hn Étale of spec of K. And for the sheaf, we take the sheaf of Lth roots of unity and tensor that N times. So you can think of this maybe as something like Z, like, it depends how you want to do it, like Z of N, I guess, in some sense, for the Étale theory. So this was like the case for L equals 2. This was like Milnor's conjecture, known in the literature. So in general, for L greater than 2, or for L odd, L here is a prime, of course. For L odd, it's called the Bloch-Kato conjecture. And sometimes collectively known as the norm residue theorem. It was proven in Vygotsky, made by Vygotsky, completely finalized maybe in 2009. And as you can imagine, like, we're gonna, one of the main steps is to relate this guy to motivic cohomology. So I guess the theorem that I want to briefly discuss is the following. So maybe sub-theorem. there if you take the nth Milnor K group, then this is the same as nth motivic cohomology, let's say, of spec of K of Z of N. Wait. So this is motivic cohomology. So, I mean, that's the current proof. I mean, the current strategy for the proof. So it's kind of cool that, like, on this side, we have something that's like Étale cohomology, and here we have something like purely algebraic in some sense, higher algebra theory, and the connection between them is via motivic cohomology, so which is this guy. I mean, then there's an extra step, like there's more work to do to prove that this is actually equal to this, but it's more kind of, this looks much closer to this as you expect. But the fact that you have K theory and motivic cohomology, it's a big literature, it's a big, I mean, research topic to always equate, find relationships between these guys. So I guess we can have a quick look at the sketch of how this theorem works, at least a map in one direction, very quickly. So sketch. Right, so I want to study maybe Hn of spec of K, the motivic cohomology of this guy. So for n equals 0, like the conjecture is trivially true, and then for n equals 1, there's a small calculation one needs to do and prove that, like, z of twisted by 1, you're interested in, like, what this sheaf is. I mean, this is not a sheaf, right? I mean, what I mean is, like, if I take, like, you know, its image in DM in the sheaf category, yeah, then this is actually equal to the sheaf of units in degree -1. So this is like a calculation. And the upshot is that h of 1 of spec of K of z of 1 is equal to h of 0 of spec of K of the group of units. So you get K star, which is equal to K of 1 of the Milnor group. So that's good. So then for higher n, for n greater or equal to 2, you need to construct maps between these two guys. So like for this map here, we need to understand, like, a little bit what Zn here is. So by some maybe spectral sequence analysis, this thing here is the co-kernel. I mean, the point is that spec of K is very small, so there is a possibility to analyze this a bit closely. It's equal to some sheaf, which I write down F, the A1 components, to F of spec of K. And this here is the difference map. So I mean, induced by, like, spec of K to A1 going to the 0 point or the 1 point, like let's call it 0 minus 1, let's say. And here, F is the sheaf of GN, so the punctured disk, self-product, n times, and quotiented out by some ideal. So some ideal. And then basically to construct a map from here to the Milnor K group, which is roughly this K star quotient, of this K star quotient out by some ideal, it now becomes possible. Like here we have like n copies of GM, and there's a possibility to map to get a natural map from here to here, of course. But then you need to check that the ideal gets sent to the ideal, and this is properties of K theory. So I mean, let's probably stop now. That's just to give an idea basically of how it works. So let's stop here. For today. Yes. Okay.